Okay, thank you for the introduction. So I would like to thank the organizers for this opportunity. So today I will talk about something which is about, we heard about imaging science. Can you hear me? Good? No, really? Is it better now? Okay, thank you. So we heard about, images, could be applied in medical science, could be applied in say the cryo-EM, and also could be used on remote sensing and biology. So we see images pretty much every day. So today this talk is about image supersolution. So which is talk about you have some images to start from. The images are very low resolution, like when you search on Google Map and you always try to zoom in. So when you click on zoom in, things are, the algorithm behind is that you have some supersolution algorithm behind that. And we're also going to touch a little bit on the application on multispectral imaging. So I will talk about what is supersolution. In particular, this supersolution is slightly different with some, maybe like Donald Hall, they talk about supersolution. Their starting point is some Fourier data, like low-frequency Fourier data, and try to reconstruct the high-frequency information. So over here, we start from images, like images which are, low resolution. We try to. It's on.
It is on, oh, okay.
Yeah. It's the volume.
That they can't hear it, so. No, it looks good, okay.
So I guess I have to speak louder, okay? Yeah, it's on. All right, so here we start from images, like daily images, and how do we increase the resolution? You can see better details. In particular, in imaging science, we care about sharpness, we care about, small details. What we're gonna do is like this. So very different from what is done in the literature. So when people think about images, we always say, oh, there's a digital image over there. Everything is digitalized. So a lot of the algorithms in the literature are based on discrete modeling, like try to reconstruct a discrete matrix. So here we try to reconstruct the analog image, which means we want to reconstruct some images in some spaces, okay, certain spaces, but unfortunately we don't know what is the best space to describe, daily images or application images. And so what we want to do is to pick up some space we kind of trust on, and we try to do some auto correction. What if the space you choose is not so good? What if you have error here? What if you have error in your computation? How do you auto correct that? So that's the idea for this work. Speaking of the analog and digital images is regarding this. So this is like an analog image, which means it's some function defined on a continuous domain, like a human brain, right? We are defining a solid, domain, continuous sort of domain. There's no gap in between here and there, right? But in digital, what you see on computers or your phones are digitalized images. So the relation between them is that the analog image is a function. Okay, z is, if it's a two-dimensional image, you have z equal to f of xy. Xy is in some domain. Usually, images are defined on a rectangular domain. And the digital image would be just some discrete values of this analog function on some discrete locations. So the relation between the low resolution and the high resolution is like this. So as I said, we start from images, not like, oops, where is this coming from? Sorry about that. Okay. So we start from an image, okay? So the image resolution is very low. So digitalized means you have a very small image, very small size. And what we want is something that the size is bigger, but it's very easy to make it bigger. Like interpolation, those sort of things can easily make it bigger. But we want to make sure the images that are bigger actually also can have a lot of interesting sharpness, features, and details, small details. So that's the idea. So mathematically, this is the relation. So you have a you have one or two or several low-dimensional images over here. Okay, so you have L means low resolution. So you have LK, which is related to the high resolution. Image size is bigger if you do a discrete setting. And the BK is a blurring operator. Because from low resolution to high resolution, very often if you just zoom in at low resolution without any advanced algorithm behind, it looks blurry. And there's a downsampling operator because you have the size is smaller. So the relation between the thing you're looking for, which is called a high resolution, and the data you have available is like this. Okay? And so in the literature, a lot of work have been done for the multiple image supersolution, meaning that you have a lot of Q. The Q is large. So you have multiple images of the same thing from different lighting, different perspective. So that's called a multiple image supersolution. Okay, multi-image supersolution. So for this problem, the data, you have more data, okay, because your P, you have a lot of lower resolution images available, so you can easily solve some sort of inverse problem to get this guy. What we are talking about today is a single image supersolution, which means you only have one low resolution image available. This could happen very often in reality, like you just have one image available, like a satellite when they take images from above of the Earth, you only have one image available. Or you do a biology study, microscopy, it's very expensive. Sometimes they have to pay to do imaging. You just have one low resolution image available. How do you make it work? How do you make it bigger? How do you make the images look sharp and have a lot of details? Okay. So mathematically, obviously, it is going to be a yield-post problem because you are trying to reconstruct a bigger image from low image. This image is much smaller. If you do 8 times enlargement along each dimension, you have 64 times of number of variables than the original available data. Okay. And as earlier we talked about relation between the low resolution image and the high resolution image, you have a convolution over there. You have a downsampling operator over there. So very often we don't know the convolution kernel. Okay, and also so the goal of this is to reconstruct a high quality image. We want to preserve textures, preserve sharpness. So in the literature, some work have been done on this. So a very straightforward approach would be to do interpolation. Okay, interpolation can fill in intensity in between grids. Okay, but you have to do it in a very smart way. Otherwise, because interpolation usually is done in a local, sort of way, so it's kind of hard to get global regularity. And there's also some example-based methods where, for example, the deep learning thing, they might fall into this category. So they do a lot of data collection. Even though I'm only interested in one, in zooming in the resolution of this one single image, they require a lot of other data from other different unrelated things, probably. Okay, so this is kind of a different approach. So you have more data, you have more power, and you have a deep learning, very powerful tool to back up with that. So that's something definitely going to be very powerful. So over here, we are talking about just one image, okay? So our idea is that we want to start from this low resolution image. Hopefully, we want to figure out a high resolution image. And our idea is to try to reconstruct the analog image. Okay, analog image means we want to get the function of the image intensity function as a function. Okay, so as a mathematician, the first question would be which space you're going to be sitting in, and how do you figure out the basis, the coefficient of the basis. Okay, so what we're going to do, we're going to borrow the tool called RKHS. Okay, reproducible kernel Hilbert space. And try to stay in that space, but this space is not 100% good yet. So we want to attach something else to particularly describe edges. Okay, because in images, what we really care is the sharpness, the details, which are mostly described by edges. Okay, so we're gonna use RKHS, which is something excuse me, to describe the smooth components. Like if you take a picture of your excuse me. if you take a picture of a human's face, so like the cheek area is like a piecewise smooth function, right? Because from one intensity to another, suppose you don't have moles here or there. So you have a very smooth, piecewise smooth function. But there is a sharp, difference from your cheek to your hair area. So you have a lot of, if you have a curly hair, you have a lot of textures, you have different kinds of orientations in your images. So we want to make sure we can take care of both the smooth components and the edges very well. Okay, so what we're going to do is to use one space for each. For the smooth components, we're going to use RKHS. For the edges, to take care of the sharpness, we're going to introduce a Heaviside function. Okay, Heaviside function. Everybody knows Heaviside function. You have a jump over there. So we're going to try to see how do we modify it to describe edges in particular. Okay, so reproducible kernel Hilbert space. I believe there's a lot of experts over here. Okay, just to be more self-contained, here's a quick review. So basically, it's a Hilbert space. So it is a Hilbert space H that has a kernel. Okay, so the kernel is able to reproduce a function f itself. Okay, so if you have an f which is in the RKHS, you will be able to reproduce your f function by simply doing inner product of your f with the kernel. Okay, so that's why it's called reproducible. You'll be able to reproduce your function itself by doing inner product. Okay, and of course this kernel has to satisfy some condition. It has to be positive semi-definite. And then you can do, the eigenfunction, decomposition. The any function f can be linearly represented by this. So this is like a basis. But do not have to worry. All the computation will be just based on the kernel. We're not going to try to figure out eigenfunctions. Okay, so everything will be done on this based on kernel. And the flexibility is that by simply choosing different kernel function, you will be able to reach to different space. It's still RKHS, but depending on how you choose your kernel, you're going to get different kinds of RKHS. For instance, if you choose your the kernel to be a polynomial of degree k, if you choose your k to be like this, your RKHS would be polynomial of degree k. Degree d, okay, which is something very nice. If you want to describe something super smooth, this would be a good choice. And some people choose like a Gaussian function. There will be a C infinity, okay. Or if you want to have some sort of, you don't want to be too smooth, then you could choose the k to be defined like this. Then you're going to get a stop-leaf space, okay. So it's very flexible. We like it because you have a lot of flexibility. And the computation is done only based on the kernel. You don't have to worry about how to find eigenfunctions. So we're going to look at, just to give you one example. So the stop-leaf Hilbert space, if you talk about, it's easier to start from 1D. So we're gonna look at the set of all the functions which are absolutely continuous up to m-1th order, and the mth order derivative is in L2, say. So because the first m-1 derivatives are smooth, you can do Taylor expansion. Okay, very simple. So you can do Taylor expansion. The first m terms would be just polynomials, and you have the residual term over here. Okay, and based on some RKHS theory, you will be able to represent both the polynomial part and the residual part as a sub-RKHS space. Okay, so both of this and both of the two components will belong to a RKHS, and you will be able to find out the kernel. Remember, RKHS, you just need to have a kernel. Okay, so we have a closed form for the kernel for both of them. For the polynomial components, you have this kind of kernel, and for this the residual part, you're going to have this kind of kernel. Okay, it needs some computation, but they're all manageable. So anyway, if you are talking about something in the stop-leaf Hilbert space, basically you have two components. You have the polynomial, which is super smooth, and you have some residual. And each one of the components has a kernel attached with it, which makes our computation very convenient. Okay. All right. So as I said, this kind of if you are satisfied with this stop-leaf Hilbert space, probably that's the two kernels you have. Then you go ahead to figure out the coefficients. Probably that's the end of the story. But if you want to apply it to two-dimensional, case, earlier was one-dimensional. You do Taylor expansion one-dimensional. If you do 2D thing, we're gonna borrow the thing called a thin plate spline, okay? Thin plate spline, because it's two-dimensional thing. And you can follow the same idea. So earlier, if you look at this thing, basically, these are the bases, right? And you just need to figure out the coefficients. So if it's a 2D, you just generalize it to change this to something else, say thin plate splines, you're gonna get something. So it still is gonna be a linear combination. So we are talking about try to reconstruct the underlying image intensity as a function. And we find a basis for the function. So what's next is going to be like use this giving low resolution image intensity, which is discrete, just a matrix, and find a relation between the matrix and the function you have. So the most straightforward way would be I have a function, right? And I evaluate this function on the discrete grids to get a discretization of your underlying low resolution image. But this low resolution image has a slight difference from the given low resolution image, because this one is ideal. No noise, right? No blurring. So you want to set up the relation between this sort of ground truth low resolution image and the given one. Okay? So so that's what give you the model. But that's still not enough, because as I mentioned, if you stay in the soft-lived Hilbert space or even the same plate splines, you're still kind of not taking care of edges or small features, very carefully. Okay, like people who are very familiar with wavelets, framelets, or shearlets, they probably they in particular shearlets or framelets, they take care of angles of different orientations, right? So so edges really are very important for images. So over here, we're gonna, because we already have a RK space over there, which takes care of the smooth components very well. Over here, we're gonna just to explicitly represent edges. Okay, so we're gonna borrow this Heaviside function. So Heaviside function is very, people are very familiar with it. It's like a switch. You have a switch turn on at the time t equal to 0, and you have a jump at t equal to 0. So 1D signal, this will give you a jump over here. So if you have a piecewise constant, you do want to preserve this kind of jump. For 2D images, we would have two-dimensional jumps. So we're going to augment this one-dimensional Heaviside function to represent jumps, edges in two-dimensional images. And before we do that, we're going to smooth this Heaviside function a little bit, because the original Heaviside function is not not even continuous. Computational-wise, it's not so convenient. So we want to smooth this a little bit. There are different kinds of smooth approximation in the literature. This is just one kind of them. Okay, it depends on how you choose your parameter. Say you're going to have different approximation. So here are some examples. How do we augment the one-dimensional Heaviside onto two-dimensional jumps? So what we're going to do is to attach this smoothed Heaviside function by this Vj dot z plus Cj. So Vj is describing our rotations. Okay, so you have a rotation two-dimensional, because it's two-dimensional images. So you have a rotation, and you have a shifting over there. Okay, so the composition of this smoothed Heaviside function with this linear function, you're gonna get affine function. You're gonna get the 2D images at with different angle at different location. For instance, over here, for these three images, you have a at 135-degree angle, and you have a 45-degree angle here, here, and here. Okay, so these are 9 different images with different edges over there. And these are the corresponding 3D surface representation of that. So you can see still sort of Heaviside, kind of two-dimensional jump over there. All right, so so Heaviside functions for edges. So what is the theoretical backup for that? Okay, so theoretical backup for that is that in this 2003 paper by Kane, they proved that a function in LP, okay, a function in LP can be approximated by this. Okay, so you could do a linear combination of this, and you will be able to represent something in LP. Okay, So what we're going to do is to kind of use this to, because in images, our intuitive motivation was we want to recover edges. We want to preserve edges. And the RKHS is just not enough for us yet, okay? So we want to attach, we're going to add this Heaviside function onto the RKHS, okay? So it's going to be a redundant. Okay, redundance, sometimes it's not good, sometimes it is good in this case, because we want to keep edges very well, but we don't know where the edges are. We probably have a rough idea from the initial given low resolution image. You can do a quick fitting to see a initial location of edges and the orientation of the angles. But we, if I don't have anything, beforehand, I don't know where the edges are. I don't know the angles of them, okay? So I would make it exhaustive, okay? So I'm assuming every location, possibly there's an angle over there, and I'm gonna consider all kinds of angles, like 0 angle, and 20-degree angle, 40, 60, 80, things like this, depending on how you choose your resolution for angles. And then we're gonna, let the data to guide us to decide where the edges are and what the angles are. Okay, so here's the model. So the T is coming from so T and the K are the bases coming from RKHS, the polynomial and the residual. And the psi over here is the Heaviside. Okay? Remember, each one of them is some linear combination. So eventually going to be a linear system over here. B is a blurry, if you still remember. D is the downsampling. And the low L is a giving low resolution image. Okay? And we're going to need some regularity, definitely. In particular, this guy over here is very wide, very short. Okay? Very wide, very short. So it's kind of underdetermined. So we need 2 pairs of regularity. This guy is coming from the residual. This is a residual. So we want these two together to describe the smoothness component. So we want the residual to be as small as possible. So this is a way to describe the residual. And this is a typical thing because the Heaviside function we used is kind of redundant. A lot of them should be 0. A lot of them better should be 0. So we should put either 0 norm over here or 1 norm or P norm. Okay, so just demonstration, we put a 1 over here. Okay. So the idea is very simple, and you could use, depending on what regularity you put over here, you could choose different algorithm to compute. If this is, 0 norm, 0 semi-norm, you probably want to use OMP, orthogonal massive pursuit, greedy method. If it's L1, you could use a prime or dual, but not ADMM, because ADMM is not guaranteed to converge for this kind of thing, 3 things together. And the computation is done by patch-wise, which means that you have a low-resolution image. You're going to divide into a lot of small patches. And you either do patch by patch or you do a classification, do a non-local classification to, to group similar patches together and run that group all together. Or you do an individual patch. That will be less efficient. And so earlier we talked about, you probably have a lot of questions, a lot of, doubt in mind. How do you know the basis you choose is good? How do you know, the low resolution is the information is enough for your model to get something reasonable? Okay, we have the same question too. So for the question of whether your basis is good or not, we're gonna do some sort of auto correction. It's very easy for you to choose something which is not reasonable for this particular image. It might be good for this image, but this basis might not be good for another image. So we try to make more self-contained by considering how do you reduce the error. Okay, so the error could come from a wrong choice of your basis, like RKHS, the kernel you choose might not be good. And it could also come from the not so perfect computation. Okay, even after you choose a perfect basis, when you solve the minimization problem, you probably end up with something not so convergent or not so accurate. So how do we sort of reduce the error? We're not going to guarantee 100% remove of the error, but we have a sort of auto correction scheme. So the idea is sort of back projection. So the idea is like this. So suppose you choose your basis, and you run your optimization already, and you get your D and C and beta, which are the coefficients of your redundant quoted basis. And but then you can create, this would be your high resolution, right? Because you have the coefficients already. You discrete, the H means finer grids. We talk about higher resolution, you have finer grids, discretization of your continuous domain. So you have finer grids, you put it back. And then you're going to get your high resolution image. But this is not the end of the story, because this might not be 100% good yet. So what we're going to do is to mimic the downsampling and the blurring operator to create something which is low resolution. Okay, start from this guy, which is something you think is a candidate for the high resolution image. And you do blurring, you do downsampling to get a mimicking to obtain a low resolution image. Then you tell the difference, okay? This should be L, sorry about that. This should be L, okay? So you, well, at the first iterate, when k is equal to 1, it's L super 1 would be just the initial given low resolution. So you take the difference of them, and you see if there's any error there, okay? If this computation was 100% good, then suppose, mathematically, when you take, because remember our original assumption is that low resolution is equal to this. And not because you don't have noise. Suppose your optimization was good, there was no noise. So if there's an error between these two different copies of the low resolution image, most likely your HK was not so good yet, okay? So what we're going to do is to rerun this algorithm and just on the difference. Okay, in your difference, it has error because you have difference. So the difference usually contain either the noise or the some features, some small scale features, details. So we're gonna put this back into the model, and we rerun it. Okay, after we run it, we're gonna get some new details. We're gonna add it back to the original image. Okay, so we do this kind of outer layer iteration sometime. So let's see some numerical experiments. And so we start from this low resolution image, which is a line. It has some features, textures on it. By the way, this is my colleague Julia's favorite. Julia was a postdoc over here. She likes animals. So we have a low resolution. If you do bicubic interpolation, this is what you get. Okay, bicubic interpolation end up with something kind of over smoothed. You don't see the features, the sharpness very well. This is the TOG work. Again, it's kind of over smoothed. It's TIP1. You gradually see some details if I go back and forth. Okay, you probably can see some details over here. See the difference. And IPOL, this is based on TV, total variation. It's kind of overcorrected. And this is TIP based on another way of using TV as well. And this is a proposed one. If I go back and forth, you probably can see the difference better. And the ground truth look like this. Okay, not so perfect yet, but we are trying to come up with something better than the state of the art at that time. All right, so we have some other numerical experiments. If you look at this bamboo, this is the ground truth, and this is our result. And you can see the difference from others. I apologize if you cannot see the difference. I don't blame you. It takes time to get used to it. All right, so here are some numerical results. Because this paper was published 2 years ago, so we compared up to here. So we have some proposed approach over here. Basically, the bolded face would be the best. Underlined one be the second best. So it's kind of consistent. So I'm running out of time, so let me briefly talk about how do we use this for pen sharpening. Okay, I know there are some, like Professor Wojciech is doing some on this as well. So So the pan-sharpening is like you have is talking about remote sensing data, okay, from satellite. So you have a multispectral, like different colors, okay, red, green, near infrared. So you also have a panchromatic. So they have two, sort of devices, to take the image of the same thing at the same time. So the panchromatic image is black and white. It's grayscale and has a better, spatial resolution. And the multispectral gives you, rich information regarding color, because different objects have different response to different color. Like trees will be sensitive in the red, in the green channel. So they do provide different layers of information. So the pan-sharpening is a problem which combines both of them to come up with something which is high resolution in both directions, okay, in both spatial resolution and spectral resolution. Okay, so our idea is very simple. This was a collaboration with Jocelyn Chernosov's group. So it's talking about, so our idea is very simple. So again, we're going to reconstruct channel by channel. For each channel of this high-resolution multispectral image, we attach it with the redundant basis we had. We try to find the coefficient for each slice. But at the same time, you want to make sure they talk to each other. Like these are all, images of the same thing, just different color, different spectral focus. So you want to make sure the coefficients, like the adjacent slices, the coefficients are similar. Okay. So as I said, the idea is going to be very straightforward. We have the same basis, but different coefficients for different slices. I want to make sure similar adjacent slices would share similar coefficients. And here's a very quick, brief example. So this is the ground truth, and we compared with a lot of them, and this is the proposed one. If you think it's overwhelming, you could focus on this, the river area. You can see the color, okay? So over here, the color looks like kind of a light, very light over here. And a lot of them are like very dark. It's kind of a spectral distortion. The color is different. Okay, so this one is kind of better. And if you zoom in, you will be able to see some special features as well. Okay, so this is some comparison numerically. And as a conclusion, what I talked about today is try to come up with some analog function of the underlying image intensity. And we choose to use RKHS plus Heaviside to describe the intensity function. Then use the given low resolution intensity to find the coefficients of the basis. Then you can apply it on other different applications. Okay, thank you.